Hey guys, Mr. Betts here. I'd like to introduce you to how we're going to do calculus on parametric equations. So hopefully you're a little bit familiar with how parametric equations work, even if it's just a basic introduction to it. Like you should have watched the previous video on me introducing parametric equations. So with just kind of a basic introduction to it, I'm going to use the same curve that I used in that video. And the calculus part of it is we essentially want to be able to take a curve that looks like this and figure out what is the slope of the tangent line to a curve like that. So even though this is not a function, we've defined this relationship here. The x coordinate and the y coordinate depends on a third variable t, that parameter. We still might want to find a slope, which is still a traditional slope in the traditional sense, and use calculus to do that. So I want you to keep in mind that when we're finding slopes in the xy coordinate plane, the slope is going to be given by the same derivative we've been using in the past. It's going to be given by dy dx, because in the xy coordinate plane, dy is a vertical change and dx is a horizontal change. So dy dx gives us a vertical change over a horizontal change, which is what slope is. So we still want dy dx, but if you look at how this relationship or this curve is defined, we don't have a relationship between x and y. And so like we might be able to take implicit differentiation and take the derivative here with respect to x to get dy dx here, but it would be messy and it wouldn't really get us to what we want. So the idea here is going to be more of an algebraic trick. And I'm going to actually do the solution to this particular problem in an example video. But the idea is if we want dy dx, and the relation is defined in a way where we can find, with this one, we would be able to find dx dt. So we can take the derivative of that equation with respect to t, because that's the independent variable here. And with this equation, we can find dy dt. And the sort of algebraic trick, and I want to be clear that doing algebra with differentials doesn't always work, so we have to be careful with it. But the algebraic trick is to get dy dx, we can take dy dt and divide it by dx dt. So we can take two separate derivatives with respect to time and then divide those to get a derivative with respect to x. Now, I want to point out, and we'll see this when we do the example, when we take derivatives here with respect to time, those derivatives are going to have t in them. So this expression that we're going to end up with for dy dx is not going to be in terms of x like we're used to. It's not going to be in terms of x and y like we've seen with implicit relations, but it's going to be in terms of that parameter t. And that's going to come into play with some of the problems that we're going to do later on in this unit. So big idea here, if we want to find the slope of a tangent line, essentially we're going to take dy dt divided by dx dt. Now, we do have to exclude points where dx dt is going to equal 0, because then we would be dividing by 0. I do want to point out that if we're dividing by 0, so if dx dt is 0 and dy dt is not 0, so if the denominator equals 0 and the numerator is not 0, it's anything besides 0, then what we're going to end up with is a vertical tangent. So the slope is going to be undefined because the tangent line is vertical. If we have a numerator and denominator that are both 0, that should look familiar to us. That's an indeterminate form. And a lot of times that happens when we actually get two different slopes at the same point. So if I go back to this example here, at this point, so that point we actually get from two different t values, but at that point we may end up with an indeterminate slope depending on how we compute it, because we don't know if we're talking about the slope of the tangent line in this direction or the slope of the tangent line in this direction. Parametric equations handle that situation pretty well, so we won't have too much trouble with that, but it could be something that we would run into. Some smaller ideas, dx dt and dy dt give us some insight into the motion of the curve. So I mentioned in the last video that parametric equations lend themselves really well to motion of objects. And that's because X and Y being independent of each other, we can model motion in the horizontal direction and the vertical direction separately. And that leads to all kinds of great applications with projectile motion and orbital motion and stuff like that. So if we look at dx dt and dy dt separately, it can tell us a little bit more about horizontal motion in the case of dx dt and vertical motion in the case of dy dt. So if we break that down here, for example, if dx dt is positive, that means that the rate of change of x with respect to time is greater than 0. So that means that x is increasing. So if we say x is increasing, that would mean that it's moving, or we have motion to the right. Because if x is getting bigger values on the x-axis are to the right. On the other hand, if dx dt is negative, that means that it's moving to the left. And the nice thing here is motion to the right or to the left only depend on the definition for x. So if we look at this example again, motion to the right or left only depends on this one. So we can simplify problems if we want to know certain things about the motion of an object. Dy dt tells us about vertical motion. So if dy dt is positive, that means y is increasing. So we would have an object that's moving up. Or if dy dt is negative, we have an object that is moving down. Now we might have intervals where dy dt is positive and then it switches to negative. And at that switch, we're either going to see a discontinuity or we're going to see maybe dy dt is equal to 0. So when dy dt is equal to 0, it's not moving up nor is it moving down. So some of the same ideas that we see with that straight line motion, but now we're talking about the motion in 2 different dimensions. So horizontal motion and vertical motion at the same time. So I want to just take a look at this and kind of talk about what that means, separating horizontal motion and vertical motion. So if you remember from the last video, when t equals 0, we got a point here at the origin. When t equals 1, we got a point, I don't know, somewhere around here. Then at t equals 2, we got this point here. It actually ends up being a vertical tangent there because dx dt is 0 at that point. And then this is at t equals 3. So you can see as time is going on, our object is moving around in this direction. Well, if we just look at the derivative at t equals 3, and I'm not going to look at specifics here, but at the point where t equals 3, what's happening here is this object is moving up and to the left. And we can verify that by looking at dx dt, and I'm going to use prime notation here, x prime of 3, that's dx dt evaluated at 3, that's going to be a negative value. So since x prime of 3 is less than 0, I don't know exactly what it is, but I do know it's going to be a negative value. That means that our object is moving to the left. If we look at what's happening with dy dt at 3, that's going to be a positive value, which means that our object is moving up. So in combination, the object is moving to the left and it's moving up, and we get together we get a slope that looks like that. So normally we think of slope as going from left to right, but we could also get a negative slope by going up and to the left instead of down and to the right. So looking at these derivatives individually help us a little bit more with the motion of the object. And in this case, tells us that the object at this point is moving in this direction.